Okay, good afternoon, everyone. We have now the second and the third talk from Carlos, with a coffee break in between them. So, Carlos, welcome back, and yes, you can start.
Good lunch.
We are not hearing down here.
Okay, let me try again.
Now, yes.
Okay, can you hear now? Okay, good. So I was just wishing everybody a good afternoon, and hope everyone had a very nice lunch. What I will try to do today is continue the discussion about supersolid phases in cold atom systems. And I would like to talk a little bit more about today over a different point, which in the first lecture I discussed the emergence of dipolar boson supersolids in the continuum, or you could think about a box trap or a harmonic trap, which is sufficiently flat. And the topic today is going to be lecture number 2. Is going to be about dipolar boson supersolids in optical lattices. So we will discuss how those supersolid phases emerge. Instead of having a box trap potential or a harmonic potential reasonably flat, how do they emerge in case of optical lattices? So let me bring these things up to speed. I have to define in the spirit of a school. I'll try to be pedagogical. And begin by discussing what is an optical lattice, and then go on to review what we know about bosons loaded in optical lattices, and then just standard bosons. Then we say, okay, what if these bosons now are dipolar? They have dipole interactions between them instead of just extremely short range or local interactions between them. And look at a specific case of two-dimensional optical lattices, and then analyze these systems in the within the dipolar boson two-dimensional optical lattices. Find out under what conditions dipolar supersolids emerge. Then I'll conclude. So beginning what I say now is some kind of tradition on my side, I would like to conclude first with begin first with the conclusions to give you an idea where we are going. So even if things are not necessarily clear immediately, I would try to build the lecture towards that goal. So let me bring you up the conclusions. So I'm going to bring the same slides back at the end of the presentation. And but just let me make the points first. What is the idea here? Well, we're going to be talking about supersolids in an optical lattice. And again, the working definition of supersolid is a system that exhibits both superfluid and crystalline order. So supersolid phases of dipolar bosons would exist in 2D optical lattices more easily. In 3D, there are some difficulties. Depending on the orientation of the dipoles, we're going to find out, and of course their interactions, that supersolid phases can arise, and there are some conditions for this to be discussed, where periods, this supersolid, this new crystalline order arises such a way that the periods of these supersolids are commensurate with those of the optical lattice. It's like a superlattice is formed, right? A structure that has periods which are commensurate with those of the optical lattice. The optical lattice is there, and all the optical lattice is providing is a length scale for which these dipolar superfluid phases, supersolid phases, can have commensurability with. In the case of the continuum, you don't have such a length scale. So, but in the case of the optical lattice, you do. Then I would just mention that supersolid phases can arise both being isotropic and anisotropic, depending on the dipole interactions in the orientation with respect to the lattice plane. So that's an interesting thing, because you can visit these different supersolid phases by tilting the direction of an applied electric or magnetic field. And that's a cool thing to do, because you can tune that direction and you're going to visit different types of phases. So just to show one example, which we're going to talk about that, we're going to have a system of bosons in a, let's say, two-dimensional optical lattice. And these bosons are dipolar in nature. So imagine that in each one of the sites here, I'm going to have dipoles. And I can imagine a situation in which I apply an external field, electric or magnetic, depending if you have an electric dipole system or magnetic dipole system. And all these dipoles are aligned with the direction of the field. So by tilting the magnetic field, the electric field or magnetic field, you can orient the dipoles in a particular direction. And of course, depending on the orientation, the interaction between them is going to be different. So what I'm showing here is just in a simple situation in which the direction of the electric or magnetic field in the XYZ axis, with the lattice being the XY plane, if I make an angle phi, polar angle, of pi over 4, or azimuthal angle, sorry, pi over 4, and a polar angle alpha, arbitrary, I can look at the interactions, create a phase diagram, where the interactions V, Y, and Vx, which are here representing interactions between nearest neighbors in the plane, they will change as a function of this angle alpha, because these are the dipole interactions. However, if I choose the angle to be pi over 4, you can show that these interactions are exactly the same for arbitrary value of alpha. We're going to show that explicitly. And the point of this slide is that if you change the direction of the field, the angle alpha from 0 to 90 degrees, you're traveling along this line in the phase diagram, and a line which the interactions Vx and Vy between two neighboring dipoles is exactly the same. So when alpha is equal to 0, I'm here at this point. This means alpha, the azimuthal angle, is 0. Clearly, the dipoles are completely repulsive because all the dipoles are aligned along the z-axis. So the dipole interaction is purely repulsive. And in this case, you have a checkerboard supersolid phase that emerges. As you change the value of alpha, as this angle is going down, the dipole interaction starts changing. Even though they're about the same, they're exactly the same, the dipole-dipole interaction start getting reduced towards 0. Okay? And it becomes exactly 0 for nearest neighbors at a critical angle, which is about 35.26, 35 degrees, which is exactly here at this point. And right there, you have a superfluid phase. On the other hand, if you keep tilting the electric or magnetic field all the way down to the plane, still along phi equals to pi over 2, this dipole interactions between nearest neighbor dipoles becomes completely always negative, and the system then collapses. So it's kind of interesting to see that by changing the direction of the electric or magnetic field, you can go from a supersolid in which you have a structure, periodicity, which is different than the lattice itself, to a system which is going to be essentially superfluid, which the occupation every site is about the same, and you have superfluid properties. And to a situation in which the interactions are completely attractive and they would collapse. Okay? So just to illustrate a point. So I'm going to come back and show several examples when this thing arises. But just to show an important point, that you can tune the direction of the electric and magnetic field, and you can visit different phases: a supersolid phase, a superfluid phase, and a collapsed phase, or a phase-separated phase. Okay, so let me then, since it's a school, let me begin by saying and describing what is an optical lattice. So an optical lattice has been realized in the field of cold atoms, of course, by using lasers, and is of course different than a lattice with real crystals, in which you have nuclei and electrons, which are bound together into a solid structure. In ultra-cold atoms, the lattice that is present there, for which the atoms can move around, is created optically via laser beam, and you can create some minima of the potential which can sort of trap atoms inside, and those atoms could tunnel from side to side of this optical lattice. So you can use neutral atoms, bosons or fermions, to do that. Of course, there's no Coulomb interaction. It's all optical. And it's different from a real crystal. Nevertheless, some of the electronic phases, or many of the electronic phases in condensed matter physics, like metallic, insulating, superconducting, ferromagnetic, antiferromagnetic, can also exist in those systems. And many examples already exist. I mean, sodium atoms, potassium, rubidium, cesium, and fermionic lithium, potassium, strontium, and the list keeps growing, can be loaded into optical lattice and being studied. So the atoms are trapped typically by the same kind of atom-laser interaction that you do in a harmonic trap, in which the electric field created by a light couples with the induced dipole moment. And the induced dipole moment is, of course, proportional to the electric field itself, where alpha is the electric polarizability, which is dependent on the frequency of the light that you shine. And the trapping potential in time looks something like proportional to the electric field square, so to the magnitude square of the electric field, and the electric polarizability. So in the case of a simple harmonic trap, potential well, we have a laser beam, we have a Gaussian waist, has some region which sort of close to focal, and you can create a well exactly by the fact that the potential here, I mean, if you take the time average, let's say, is going to be proportional to the intensity of the field. So if alpha of omega is positive, high field intensities reduce the potential which the atoms can be, and that creates a trap. So a potential well, the atoms can fall here if they go sufficiently slow through the path of this beam, they just get trapped. And of course, you can have several types of optical lattices. If you have now standing laser standing wave in one dimension, you can create an interference pattern in which you create several traps nearby with a periodicity. And then you can do that instead of only one, you can put two standing waves in orthogonal paths. You create another optical lattice, and you can put three of them and create different optical lattices. So you can create clearly two-dimensional, sort of more or less one-dimensional and three-dimensional optical lattices in using laser light and interfering laser beams counter-propagating to create a standing wave pattern. So the case of bosons in optical lattices was sort of the first one which was studied and then carefully, in which case, if you look at the potential and you average over time, you can get a two-dimensional, two laser counter-propagated laser beams, create some kind of two-dimensional optical lattice in which the atoms in red can occupy different lattice sites. So for example, and that's the first case that was investigated, the case of rubidium-87, you can have lattice depths. These lattice depths are essentially controlled by the intensity of the laser beam, so the electric field square. And when you create this potential which the atoms can see, you have these two counter-propagating beams, and the period in which this lattice is directly related to KL, which is going to be the wavelength, the wave number associated with the photons, with the light. The lattice spacing, of course, is going to be half lambda L. So if you use rubidium-87, typically you're using a laser with a wavelength of about 850 nanometers. The lattice spacing is about 425 nanometers. The recoil energy expressed in terms of the wavelength is going to be something of the order of 150 nanokelvin or 3.2 kilohertz. So those are the network scales if you're using rubidium-87. Okay, so optical lattice can be created, and the lattice spacing is going to be related to the laser light and so on. So now what can you do once you created optical lattices? Well, you can put and load atoms into them and study quantum phases or phases of these atoms. So let me look at the case of bosons, because I'll be talking about bosons only in this presentation. So in principle, you can create a lattice which is very deep. So if the intensity of the beam is extremely deep, so several recoil energies, which are the natural length scale, energy scale, then if you imagine that you can put atoms inside of bosons in this case, and you put one atom on a site, it's the possibilities in which these atoms can hop from site to site, and there's a hopping energy associated with that we're going to call T. And you can also put another atom on the same site. Let's say that those atoms for the current presentation do not have yet any internal degrees of freedom, say a spin 0 boson or a boson with only one single atomic state selected. If you try to put both of those atoms on the same place, then there's an energy cost, U, due to the local interaction between them, that they have to pay. Now, when you have a deep lattice in which this depth is very, very, very large in comparison to the recoil energy, let's say, then the U, the repulsive interaction on site, tends to be much larger than the hopping energy to go from site to site. And those things can be analyzed by looking at a tight binding description of that. ER here corresponds to the recoil energy given by the wavelength of the light. And as you increase the depth of the potential V0, which is proportional to the electric field of the laser light squared divided by the recoil energy, you can see that the hopping energy decreases as the lattice gets deeper, and the repulsive interaction increases as the lattice gets deeper. So the relevant parameter is going to be then, of course, U over T or T over U. And you can see that when you combine those two things together, which can be analyzed independently, and you compare that with the lattice depth in units of the recoil energy, you can see when the recoil energy, when the lattice depth is very small, the ratio between U and T is very small. So in this case, the system is dominated by the hopping or by the kinetic energy. So you expect that when T is much larger than U, you're going to have a superfluid ground state. That is, you form a Bose-Einstein condensate. There's some interactions to stabilize the Bose-Einstein condensate, and that then leads to a superfluid state. But those atoms can hop around. And as can hop around, it leads to gapless excitations, a compressible system, but long-range phase coherence and superfluid currents. So in this case, the average number of particles could be, let's say, you should take 1. The fluctuations in the number of particles per site is going to be comparable to Ni. So this means they can move around quite a lot. On the other hand, if you are in a regime where the lattice depth is very deep, then U over T is quite large. That means that the repulsive interactions, U, are much larger than the kinetic energy. In this case, if you take an average number of particles equals to 1, the fluctuation in the number of particles is essentially 0. So what that does, it leads you to a situation in which the system has gap excitations, so the system is incompressible. There's no off-diagonal longitude order and no superfluid currents. This is going to be a Mott insulator state. So you can see that by tuning the lattice depth or the laser intensity, you can definitely go from a regime in which the system is a superfluid, when the lattice depth is very small, to a Mott insulator when the lattice depth is very deep. And of course, to describe this kind of situation, I'm going to mention an early work was done in the context of mathematical physics, which analyzed this problem. But But the simplest model to describe those things is, of course, then to say I have my bosons with no internal degree of freedom. So like I effectively spin zero boson, one hyperfine state, one state of the atom of the boson there. The notation here, the star here at this level represents a dagger. It's just that I didn't have the time to correct these old figures. You have a kinetic energy that tells you that you can hop from site to site. J and L are site numbers, locations. Repulsive interaction U on site between the bosons. This is the number of bosons on site J, and this is the number of bosons on site J. And of course, you have a chemical potential that you can fix the number of bosons by working the grand canonical ensemble. So bosons without internal degrees of freedom, that's the famous Bose-Hubbard model. And if you consider that on each site, labeled by position R, you have n particles, and these n particles are everywhere the same, if you consider that the hopping to be zero, this kinetic energy term is completely absent, and the Hamiltonian is completely local. So you can exactly solve the problem, this limit, of course, and find the ground state energy, which is going to be then a function of U, the occupation on each side, and the chemical potential. So from that, it's easy to plot the ground state energy as a function of mu over U, the chemical potential. And those lines here represent the ground state energy, which I just listed here, for different values of n. For n equals to 0, the energy is here. For n equals to 1, the energy is the purple line. For n equals to 2, the energy is the yellow line. For n equals to 3, it's the blue line, and so on. And at these points, or at these places, marked by the red, or by the red dots and by the green dot, you have transitions between phases as a function of mu over U, where the occupation per site changes from 0 to 1 to 2 to 3 to 4. So what that does, in a phase diagram of mu versus U, the chemical potential divided by the local energy, versus T over U, you have boundaries between insulating phases which occur at exactly when mu is equal to n, the number of particles per site times U. And so we have n equals to 1, n equals to 2 are not insulating states. There's no kinetic energy. So there's no way the particles can hop from site to site. There's a gap in the excitation spectrum. But then you ask yourself the question, if I introduce a little bit of kinetic energy, what happens to my system? If the kinetic energy is sufficiently large, can I have a superfluid? That's what we expect to happen. So the way to do it, to analyze this problem, is then to say, let me look at the Bose operators. Let me say there's a Bose-Einstein condensation plus some fluctuation term in the Hamiltonian, and look if the system can establish a superfluid phase. And if you do that, you can compute now the ground state energy in terms of this order parameter for superfluidity psi, and write down and obtain Ginzburg-Landau ground state energy, which has two different types of configurations. If the coefficient A2, which depends on the density and the hopping, is positive, there's no superfluidity. However, when it's negative, you have a finite psi 0 and superfluidity arises. So this means that the phase boundary between a superfluid and an insulator happens when this coefficient A2 is equal to 0, which means there will be a relationship established between n, mu, and Tu that will tell you what those boundaries are. You can do the same kind of analysis between places in which the exactly at mu equals to nu, which is a degenerate system. Then you have to do a degenerate calculation. You can also obtain the ground state energy. And what you obtain is the famous phase diagram obtained by Fisher and collaborators, which I'm going to cite in a moment, which shows that as you change the chemical potential, and as you change T over U, which can be done in an optical lattice, you may be able to visit different phases, multi-insulating phases, crossing through some superfluids if you change mu over U with T over U fixed. Or you can visit different phases by fixing mu and changing T over U. So we can go from a mod to a superfluid phase. This, of course, is the famous result from Fisher and collaborators in 1989 in the connection to condensed matter physics, in which you then have several Mott insulators and a superfluid. So the question is, can you see something like this with cold atoms? And the experiment was done very beautifully in the group of Emmanuel Bloch in 2002, in which they created an optical lattice and then tried to understand what is the characteristics that they would see in time of flight if you have a Mott insulator or a superfluid by probing essentially the momentum distribution of those systems in time of flight. So what they see then is, of course, since you can control the lattice depth of the system, and therefore you can control T over U, they start loading the systems that you have in your optical lattice with different values of depth potentials, the lattice depth, from 0 all the way to 22 recoil energies. And then you can see at very low recoil energies, you can see very clearly the, let's pick up the center one, the peak associated with the superfluid at the center, at k equals to 0, the momentum distribution, where the states at k equals to 0 pile up. It's piled up here. This peaks here, of course, shows up because of the lattice. There's the little peaks associated with the lattice structure. And as you increase the depth of the optical lattice, you can see that there's less and less coherence from the central peak goes on until all this other, when you go very deep, you lose completely phase coherence of the system, and you reach a situation in which you have a Mott insulator. That's the typical characteristics that you would have for the momentum distribution of a Mott insulator. So as you go through somewhere, maybe around here, 16 ER, you have a transition between a superfluid to a Mott insulator. And that means that you have crossed this phase diagram, let's say at some point here, along the T over U line. Superfluid for small lattice depth, and then you go to a Mott insulator for larger lattice. So that's a very nice experiment with beautiful results. And then the question that arises, of course, is this the end of the story for bosons in optical lattices? So, so then we can ask ourselves theoretically, if you had more internal degrees of freedom, not only a boson with spin 0, but you have dipolar bosons. You have some dipolar bosons in the sense of either having a magnetic moment or having an electric dipole moment. What could happen in those systems? Are there any interesting things? So far, you have a superfluid and a Mott insulating phase. So we took a look at this problem several years ago, in which we analyzed the case of supersolid and superfluid phases for dipolar bosons in optical lattices. So in particular, the existence of some checkerboard and stripe phases, as well as collapse, and the idea that you can use the external electric or magnetic field and tune its direction to visit these different phases. So you can have very nice phase transitions between these different types of systems by just tilting the direction of the electric field with respect to the lattice plane. So the phase diagram that we just saw in the case of bosons without any kind of spin degrees of freedom or dipole degrees of freedom is this one. And I'll just make a small change in notation here from T to J. I think J is the preferred notation for the hopping in cold atoms. But if you plot mu over U versus J over U, you can have this Mott insulating phases n equals to 1, 2, and 3 in the superfluid. In this presentation, I'm going to be focusing a little bit more on the region in which you have introducing electric dipoles or magnetic dipoles, so these internal degrees of freedom into the system, in which, of course, the candidates for this kind of things will be atoms with large magnetic dipole moments, atom nuclear molecules with permanent electric dipole moments, or Rydberg atoms. Anything that has a dipole moment that's large enough, it's a fair game. So let me just go to here then. So then the idea here that we want to use is getting these dipolar bosons. So we have now additional degrees of freedom in the system. Load them into a 2D optical lattice and apply an aesthetic field, E or B field, depending on magnetic or electrical or magnetic dipole moments, in such a way that you align the dipoles. Why do we want to do that? We want to do that because we want to have control over the dipole interactions. If you put in a three-dimensional structure, it's going to be very difficult to control the dipole-dipole interactions, because in some ways the interactions will be attractive in one, out of the plane, and be repulsive within the plane, and then it's very difficult to control them that way. But if you have a two-dimensional system and you apply a E field, you can control precisely the interactions of those systems. And so the idea here now is that instead of having what we had before, that this bosons here on a site had no internal degrees of freedom, this J and L has also internal degrees of freedom associated with them. And we add a term which involves the dipole interaction between them, which is described here, in which dipole interaction in a two-dimensional plane can be precisely written in terms only of the angle between the dipoles and the direction of the vector RJ/RL minus RL, which is the distance between them. So that's the advantage of having a two-dimensional configuration, is that that direction can be controlled, theta can be controlled by the application of an external electric or magnetic field. So that's one of the main reasons why we want to study that, is to have this control. And of course, it simplifies the calculations also dramatically. But the key point is the control. So we have now this new degree of freedom, which is the interaction between the dipoles. Now, there was a very beautiful experiment by Tim and Fow's group back in 2007 in chromium-52, in which they already showed that chromium is one of the dipolar systems with 6 Bohr magnetons of magnetic dipole size, that he could control the relative strength of the dipole-dipole interactions and the contact interactions. The contact interactions are described here by the little spheres, white spheres. And what that led then to some kind of anisotropy of the interactions, because you reduce the effect of the isotropic local interactions and you enhance the effects of the dipole interactions, which are anisotropic. So this was a demonstration that you can tune the ratio between long-range and short-range interactions using Feshbach resonances. And this is, of course, in a trap, but you can do the same thing in an optical lattice, a harmonic trap, but you can do the same thing in optical lattice. So then what we see then is that it's possible to have an experimental control of the ratio between dipolar interaction and the local interaction. That's one thing, by using Feshbach resonances. In addition, you could have also a control, in the case of a lattice specifically, of the sign and magnitude of the interactions due to the direction of the externally applied field, which you can vary. So just to illustrate an example here, if you pick up X, Y, Z, and here's your two-dimensional lattice and the little dipoles everywhere, you apply a field in which the dipoles are aligned, all of them are aligned, you can immediately see that the dipole interaction, let's say, pick up 2 dipoles here and here along the Y direction, can be written between nearest neighbors, for example, as the dipolar energy, d squared divided by a cubed. So d is the dipole moment, a is the separation between the lattice sites, and you can see that the dipole-dipole interaction can be written in terms of 2 angles, the polar angle alpha and the azimuthal angle, right, along the Y direction, and the same thing for along the X direction. And of course, depending on these angles, those interactions can be attractive or repulsive. And controlling these interactions then surmounts essentially to adjusting the direction of the electric or magnetic field. So then we go back to our case of bosons without structure, and what we're gonna do next says, well, we're gonna look at the case in which you add dipole interactions. And what we're gonna do then is analyze first the interesting region for us first. Of course, I won't describe here what happens in close to the Mott regions. We have a separate paper on that, but I thought was too much. I'm gonna be mostly interested in the regions where the system is superfluid. Why? Because I'm going to be interested in the emergence of supersolids out of the superfluids in the regime in which the superfluid exists. So this means that I'm at values of J over U above the critical values of these lines, and such that they're not super large as well in comparison to the filling factor, or N or nu. So we're going to describe the regions of the superfluid region in this case. So then the idea is that I want to look at how the supersolid phases emerge due to dipole interactions in the regions where the system is initially superfluid. So the way you want to look at this then is to say, I have a kinetic energy, I have a on-site repulsive energy, I have a dipolar energy, I have a chemical potential. And since I have a superfluid as a starting point, so I have to satisfy these conditions for this to be true, I can again say that I have a Bose-Einstein condensate plus fluctuations in my system, and I analyze the properties of that superfluid in terms of a local order parameter, J. I cannot take it uniform. If I just take uniform, of course, it's going to be a superfluid, but I'm allowing non-uniformity of the order parameter. And I analyze what this energy for the ground state would be as a function of T, U, and the dipole interaction. So if you do that, of course, there's several candidates of phases. If the system is completely uniform everywhere, then you have the classical superfluid. So the order parameter is uniform, and you have phase coherence across all these different sites. And the system has, with interactions, of course, is a superfluid. Without interactions, it's just a Bose-Einstein condensate. And you ask yourself the question, are there any additional phases beyond that? So in particular, you ask yourself the question, do dipole interactions can stabilize phases which have non-uniform periods, non-uniform densities, which are commensurate with the underlying lattice. So we can look at the case of a checkerboard solid, in which this case the periods will be exactly the same along the x and along the y, along the x and along the y direction. You can also look at cases in which the system is anisotropic, in which the periods are not the same along this direction. In particular, the case where the period is actually very, very anisotropic or exists only in one direction. So the system is essentially a super fluid in one direction, and has a modulation in the other direction. It's super fluid in both, but with a modulation in one direction. And that's called a striped supersolid. And that stripe, of course, in a square lattice can be along the x or the y direction. So you can look at those possible phases as well and see if they exist and they are stable. So what we find then is, by looking at the ground state energy, is that indeed, if you look at the interactions, the dipole interactions, and create a phase diagram by looking at the interactions between neighboring dipoles and create the phase diagram based on that, dividing by U, where U is going to be your unit of energy, the local interaction, you have situations in which, when these interactions Vx and Vy are the same, you have a checkerboard potential. The superfluid occurs when the dipole interactions are within a certain range, so around 0. But if eventually, when they are negative, the system would collapse. The bosons would try to go together into a collapse state, because you only have dominating attractive interactions, so you cannot avoid that. But on the other hand, if the interactions are anisotropic, are different, Vy is larger than Vx on the positive side, you can see that there is a modulation along the y direction that can occur. If Vx is larger than Vy on the positive side, you can have a modulation, a supersolid phase along the x direction, modulation as well. So the idea then is when you compare the energies of those systems, the dipole interaction, because of this anisotropy, can produce phases which are supersolid and isotropic, or if you remain over a certain range, even though with some anisotropy of interactions, you still have a checkerboard solid, supersolid. So there's a checkerboard type phase, and then if your anisotropy gets stronger, you have either a stripe along the x direction or a stripe along the y direction. So to see that, that you can visit those, how do you visit these phases? I mean, you obtain that by doing a calculation of the energy of the ground state, and you want to see how you visit them. So clearly by changing the ratios of Vx and Vy divided by U, right? Depending on Vx and Vy, you can be here, you can be here, you can be here, you can be here, you can be here. So if you change Vx and Vy, you can definitely visit these different phases. And the other way is to remind ourselves that Vx and Vy themselves are controlled by the angles alpha and phi, which the electric field makes in comparison to the XYZ coordinate of the system, or electric or magnetic field. So let me take a look at this thing and see that these interactions between the neighboring dipoles is exactly written that way. The sum of those two interactions is completely independent of the angle phi. And what I want to do is to say, as I tilt, as I change the direction of the applied field, which this will be the direction of the dipoles, how do I visit this phase diagram that was just obtained? So let me pick up an example in which the external field is exactly at an angle, azimuthal angle phi equals to pi over 2. So there's a component here. And there makes an angle alpha with the z direction. So all the dipoles are pointing along the direction of the field at phi equals to pi over 2. So if phi is equal to pi over 2, the cosine of the azimuthal angles is 1/2, and so these two interactions are exactly the same. Vx is exactly equal to Vy if the electric field is applied along that particular direction. So this means that the interaction can be parametrized by the polar angle of the field, sine of alpha. So here you can see, without recalling that V of x is equal to V of y, when phi is equal to pi over 2, and alpha is arbitrary, without recalling that, you can see that you can visit these different regions by changing u, because u is the scale. If Vx over u is 1, and Vy over u is over here, you are in this phase. If you change u a little bit, bring it down, you're going to move somewhere around there, and then you have a different phase, right? So you can clearly changing u is going to be changing where you are in this phase diagram. But I want to talk about the more interesting aspect, which is if you change alpha, also is going to be telling you where you are in this phase diagram. In this particular case, V of x and V of y are the same, so changing alpha means that you're going to be exactly along this line, where Vx is equal to Vy. The neighboring interactions are exactly the same dipole interactions. And so by changing alpha, if alpha is exactly equal to 0, the interactions are purely repulsive. The field is along the z-axis. I'm exactly at this point, so I have a checkerboard supersolid, which is my stable phase. So if I do an experiment, and I have a microscope, let's say, I would see a pattern like this. On the other hand, I start tilting the field. And as I start tilting the field at about 30 degrees, at 30 degrees, the system goes from a supersolid to a superfluid, which is around here. So it changes from this pattern to that pattern at 30 degrees. So I'm right here along this line. And I keep increasing a little bit, of course, making the neighboring interactions to be 0. The center of the superfluid box happens exactly when interactions are 0. So I'm still there in a superfluid happy. I keep changing the interaction, the angle towards 90 degrees. And before I get there, about 40 degrees, these interactions get out of the stable superfluid region and the system collapses. So you have some kind of collapse of the phase, no longer superfluid. You have some phase separation, things like that, that can occur. So, and beyond that, the system is not stable. There's no superfluidity, there's no super solid phase. So beyond this critical angle of about 40 degrees. So you can do also something similar, of course, in which you can change the thing by saying, well, let me now put in another field orientation. Let me say that I apply now the external field at alpha equals to pi over 2, so anywhere along this plane. So if alpha is equal to pi over 2, Vx can be written like that, right? I replaced alpha phi over 2, and Vy is equal to that. The sum of those two is a negative number. And you can see that in this case, there's no stable phase. The system collapses always. So if you apply a field there, no superfluid, no supersolid, the system just had purely attractive, two strong attractive interactions and collapses. Then you can look in another direction. Let's say they apply the field in the xy plane, xz plane, but with phi equals to 0. So in this case, Vy is a constant, just controlled by the dipole interaction. Vx depends on alpha. So in this case, you're going to start crossing a line, which is this red line, where the dipole interaction between neighbors along the x direction is positive for you here. When alpha is equal to 0, you are in the checkerboard supersolid. And as you change alpha, right, you're going to cross a line, which is about 30-something degrees, also here, to a supersolid, which is striped. So you're going to go from this phase to that phase. And as you keep pushing the angle to 90 degrees, again, the system collapses. So it's not stable. None of those phases is stable. And you can do the same by now applying the field in the zy plane. So phi is equal to pi over 2. And the situation is, of course, reversed by symmetry. X becomes y, y becomes x. So the interactions between the neighboring dipoles switch. And of course, the value of the neighboring interactions is repulsive, in this case, along x. It's anisotropic because x is different than y, but you're changing along this line. So if you have an angle of 0 degrees, you are again in a checkerboard situation when alpha is equal to 0. So everything is on the top, purely repulsive interactions, you are back to the same place. On the other hand, as you change the angles, alpha towards the plane, you're going to change from a checkerboard supersolid to a striped supersolid at about 30 degrees or so. And then as you keep tilting the angle further, you're going to change from a striped supersolid to a collapse phase because the interactions are too attractive. And so you can visit these phases by going this way. So you can see that by tuning the direction of the electric field, you can get different supersolid phases visible. Okay, so let me just make this point then now. What's the main message that I wanted to say today is that if you include now analyzing the emergence of supersolids, defined as a system that exhibits both superfluid and crystalline order, supersolid phases exist in the case of dipole bosons. They do not exist if you have completely local interactions or bosons without internal degrees of freedom. With local interactions, they don't emerge in that phase diagram, but they do here when you have additional degrees of freedom, like dipole interactions. And I depending on the orientation of those dipoles and the interactions, you can have several supersolid phases, and the periods are commensurate with the underlying lattice. But you can have phases which are striped, which are checkerboard, and even other periods. And to visit them, you're going to see that these isotropic or anisotropic phases, you can rely either on changing the local interaction by changing the depth of the potential, or by changing the orientation of the dipoles with respect to the lattice plane. That is, change the orientation of an electric or magnetic field. And as an example of a figure that I wanted to point out to you, is that I chose a simple example in which if you put the electric field or magnetic field with a phi angle equals to pi over 4 and alpha arbitrary, you can visit these different phases by simply tilting the direction of the electric or magnetic field, and you should see a checkerboard, superfluid, or collapse phase. And depending on the orientation, you can also visit the supersolids, striped supersolid. So I will stop here and just mention that in the next lecture, I will talk about supersolids in spin-orbit coupled bosons. So thank you for your attention.
Thank you, Carlos. Do you have questions from the audience? Yes, please.
So, hello, good afternoon.
Hello.
First of all, thank you for the nice talk. And I would like to know about the specific technique used to build these diagrams of a supersolid to a superfluid, those lines, if you use a Bogoliubov approach, if they are built using a numerical approach, or if there is an analytical answer.
Yeah. Okay. Thank you very much for the question. In this, what I talked about today is basically using the Bogoliubov approach. Huh? So in the same paper that I referred to, we analyze things a little bit further by including also fluctuations within this approach. So it relies, the results that I presented to you include both, include full dipole interactions and simplification of that, including just nearest neighbors. But the approach discussed is completely related to the idea that you start from a superfluid state. So we use Bogoliubov theory plus fluctuations to describe that. So improvements, I mean, of course, you can make on those things is to try to use other methods, numerical methods, to describe those things. But what we did mostly was analytical work with some numerics at the end to gain some insight. So a lot of the things that I mentioned to you, for instance here, these things can be obtained analytically. Yeah.
Further questions?
Would be a good candidate for improvements of those things.
So I don't see any further questions right now. So we'll be back at 4 for the Carlos' last talk. Now we have coffee, and let's thank Carlos again.
Okay, thank you.